Hey guys, we're going to jump into our Algebra 2 lesson, section 1-3, and this is called Extrema and End Behavior. So on a piece of paper, I'd like for you to take a second to do this warm-up, pause the video and try to complete the problems and then unpause it to check your answers. All right, so let's look at the answers. We've got -3, -4, -3, 4. It's symmetric about the axis, 3, 4, and it's symmetric about the y-axis, -3, -4. So we are going to move right on into the lesson. Let's look at today's vocabulary. I just kind of buzzed through those things. But we're going to make sure that we have the vocabulary because you will be having a vocabulary quiz next Friday. So make sure that you are getting the vocabulary done. Making flashcards, doing a Quizlet, however you want to do it. There is going to be a vocabulary test. So here are your vocabulary words. Once again, you can pause the screen and write those down, or you can look in your student workbook. They are can be found in the workbook as well. So jumping into page 23 on your student workbook, we're going to look at extrema of functions. So graphs of functions can have high points, they can have really low points, and this is where they reach a maximum at the high point or a minimum at the low point. And the maximum and the minimum values of a function are called the extrema. So looking at this graph right here at the bottom of this parabola, point A would be my minimum value, right? So point A is a minimum. Point B is a maximum. Point C is a minimum. Looking at each of these, we've got different things to look at. Maximum is the highest point on the graph. And I said that B is a maximum. If we look on either side of it, it is the highest point, but it's not truly a maximum because if you look at this graph extends forever and ever and ever up this direction. So we can see that it's getting higher and higher and higher. However, it's a relative maximum because in regards to the points on either side of it, it is the highest point. Same thing with minimum. This is considered a minimum, but C and E are not necessarily considered minimums because there's lower points on this graph. All of these going down forever over here are lower than point C. Same thing with point E. All of these on either side are lower than E, but this E and C are called a relative minimum because the points on either side of them are lower. So A is a minimum. A is also considered a relative minimum. And then, of course, we have our extrema. This is the highest point on the graph. This is the lowest point on the graph. And then our relative extrema are in regards to the points surrounding either side of them. So these are my relative extrema. So it's important to watch out for. Sometimes we will not have any extrema. There is no extrema here. There's no point that's considered to be a really low point on the graph or considered to be a really high point because it's going up forever in one direction. It's going down forever in the other. And then, of course, I like to look at these little study tips. In this context, extrema is the plural form of an extreme point. The plural of maximum and minimum are maxima and minima, respectively. That's just a little terminology to help you out here. So at the bottom of page 23 in your workbook, we're going to work through these examples. It says, in the sketch, drag the point across the function to identify extrema and estimate the x and y values of the extrema round to the nearest tenth. So we can see that this down here is going to be an extrema. It looks like when x is at 0, y is at -5. So that is the extrema of this function, which is exactly what it says here. Further, 0, -5 is the lowest point on the graph. So not only is it our extrema, it is our minimum value. All right. Let's let's see what this arrow is. G of x. Let's look at g of x, the next function. We've got b. We can move it up here to this extrema. So it looks like we have right around 2 maybe. Negative 2 is up at positive 8. There's no points on either side of it that are higher than it. Therefore, this is called a relative extrema. Let's see here. The function is increasing as it approaches x equals negative 2 from the left and decreasing as it moves away from negative 2. Further, there's no greater y value surrounding it. However, it's not the highest point on the graph, so we can't say it's the maximum. Instead, we say it's a relative maximum. Okay, looking down here at my relative minimum, it's not the lowest point on my graph, but it's the lowest point right here. The point over here would be higher, the point on this side would be higher, so this is a relative maximum at probably 0.4 maybe, or yeah, there we go, at 0.4. So this is a relative minimum value. All right, and now let's look at our function h of x. We can see here we have a relative max. See if I can get it to, I don't know exactly, somewhere around in there. That would be a relative max. This would be a relative minimum. We've got a relative maximum and a relative minimum. So we have several relative minima and we have 2 relative maxima. And those are our extremas. Okay, moving along to example 2, following along in our workbook. This is kind of a dry lesson. I'm sorry, I'm not real animated today. Not really sure how to make this more exciting. It is what it is. It's just some vocabulary, some new vocabulary that maybe you've not seen before. So the number of posts sent on a popular social media site varies throughout the day. We're getting a little more exciting, talking about social media. Move through the categories to see how to use the table and graph to estimate the extrema of the function that relates the number of hours since midnight x to the number of posts being uploaded y in hundred thousands. Describe the meaning of the extrema in the context of the situation. So let's look at this. We've got our maxima. Will drag me down here. What do you think the maxima would be? Well, it looks like we're going to have an exact maxima. This is the highest point on the graph. It's not relative because it doesn't extend up in both directions. This is the maxima. So my maxima would be here, it looks like at 1211.5 if we're looking at the table. That is my maxima. Looking for my minima, where is my lowest point on the graph? Looks like it would be here when x is 4 at 1.8. Looking at these values, we can tell this is the lowest. So let's go back and read this here. Says the maxima is the number of posts sent 12 hours after midnight or at noon, and it is greater than the number of posts made at any other time during the day. Therefore, the maximum occurs at noon when 1,150,000 posts are sent. Okay, so back to my minima. Basically, we can sum this up and say the minimum occurs at 4 a.m. when 180,000 posts are sent. It kind of makes sense. Who's going to be sending out a bunch of stuff at 4 a.m.? Not me. I'm going to be sleeping. My relative maximum. The relative maximum is the number of posts sent 16 hours after midnight. That's this point right here. It's a maximum in regards to the points on either side of it, but it's not the true maximum because that would be this point over here at 12. So therefore we call this a relative maxima. So it's 16 hours after midnight or at 4 p.m. and it's greater than the number of posts made during the surrounding times. So a relative maximum occurs at 4 p.m. when 1,020,000 posts are sent. And then our relative minima, this is a low point on the graph. It's low considering the points on either side of it, but clearly this is lower. So this is just called a relative minima. And it says that therefore the relative minima occurs at 2 p.m. when 910,000 posts are sent. Okay, let's do the check. Take a minute to pause and complete the lesson check there in your workbook. I'm trying to find where it is. It might not be here just yet. Let's see, lesson check. Where are we? It is at the bottom of page 26. So don't do it yet. We'll come back to the lesson check. Sorry. Let's look at some end behaviors and what end behaviors look like. What are end behaviors? Some important vocabulary. End behavior is exactly what it sounds like. What's happening at the ends of the function? Are they going up forever? Are they going, one end's going down, one end's going up, both ends are going up, both ends are going down? When we're in class, in the past, I've always done an activity called Dancing with End Behaviors, and I put the function on the board, and everybody has to stand up, and I play some music, and probably won't have a chance to do that, but we'll do both ends up, both ends down, one end up, one end down. That was how we always did it before, to try to be a little more enthusiastic about our math learning. Students are going to complete guiding exercises through the Explore activity. We're not going to do all of that, but let's go ahead and look at this real quick. We've already talked about minimums and maximums, and now we're going to talk about end behaviors. You can see as A is moving to the right, what's happening to the values of Y? As X increases, Y is increasing. But what happens as we move to the left? As X is decreasing, Y is decreasing. So let's look at another problem. What is happening as X increases? My X's, if you look, I'm pointing to it like you can see me pointing to this over here. As my X values are getting bigger and bigger and bigger, my Y values are also getting bigger. But there's something to notice here. As my X's get smaller and smaller, they're going down in the negative direction, my Y's are still getting bigger because my ends are both up. So it makes sense. As X is getting bigger, Y is getting bigger. And as X is getting smaller, my Y's are still getting bigger because it's a parabola. So this is a both ends up. We're looking at the function. We know there's an X squared in there. Both ends are up. Okay, let's look at, that's all there is to look at for this one. So let's look at an example. Well, let's get some definitions first, sorry. The end behavior is the behavior of a graph as X approaches positive or negative infinity. As you move right along the graph, the values of X are increasing towards infinity, looking at f of X. X is going towards positive infinity this direction. What's happening to Y? It's going to positive infinity. And this is the notation we use. As X approaches, that arrow means approaches positive infinity, my f of X is approaching positive infinity. But on this side, as X is approaching negative infinity, f of X is approaching negative infinity. Looking at g of X. As X is approaching positive infinity, g of X is decreasing. It's going down. So g of my function is going to negative infinity. And same thing with, well, this one is not going to negative infinity. Look, it's approaching an asymptote, and we'll get more into that later. But it's approaching this horizontal line here, whatever this value is of this horizontal line. So as X is going towards positive infinity, we say that our function is approaching a value C. So h of X approaches C. Let's look at the other side of things. As X is going to negative infinity, what's happening to f of X? It's going to negative infinity. It approaches. That's why we do the arrow. It's approaching it. As X is going to negative infinity and g of X, g of x is going towards negative infinity, approaches negative infinity. And in h of x, as x is going towards negative infinity, my h of x is going up forever and ever and ever towards positive infinity. So example 3 in your workbook on page 25, we're going to describe the end behavior. So as x approaches positive infinity, my f of x is approaching negative infinity. As my x values move to the left, they're going down towards negative infinity. My y values, or my f of x, is approaching positive infinity. Looking at this one. As x goes to positive infinity, my function is equal to 2. So, as x decreases, it's still equal to 2. As x increases, g of x is still equal to 2. So no matter what value x is approaching, if it's approaching negative infinity or if it's approaching positive infinity, we can see that g of x is always going to equal 2. All right, and example 4 with our end behaviors. Describe the end behavior of each nonlinear function. I would love for you to pause this video, try this on your own, fill it in your workbook, then unpause it and check your answers. Okay, so here we go. As x is approaching negative infinity, as x is moving to the left, these are my x values. What's happening to my y values? They're going up, 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 up. What is that called? That's called approaching positive infinity. Oh, but I looked at the left. My bad. Oh, yeah, that's right. As x is going to negative infinity, there we go. Okay, sorry. As x is going to negative infinity, f of x is going up. But as x is approaching positive infinity, my f of x is still going up. So it's still approaching positive infinity. So there's our answers. And looking at this one, as we move to the left, it's decreasing. As I move to the right, it's increasing. So we say that as x approaches negative infinity, going to the left, my g of x also approaches negative infinity. And as as x approaches positive infinity, that g of x is going up. So it is approaching positive infinity. It's a beautiful thing. All right, so now what I would like for you to do, there is a lesson check at the top of page 26 and one at the bottom of 26, but we're going to work through example 5 and then I would like for you to do that lesson check. It says the graph shows the altitude of a drone above the ground, f of x, after x minutes. So f of x shows the altitude of it above the ground and x tells me how many minutes have passed. Describe the end behavior of f of x and interpret this in context of the situation. So look what's happening. My drone's going up and down and up and down and up. It looks like it's going to keep going up. So since the drone cannot travel for a negative amount of time, you see that my graph started at 0, 0. Doesn't make any sense to talk about the drone flying after negative seconds. That's not happening. Once it starts flying, it's flying. My x's are only going to go in the positive direction. So my end behavior, there's not going to be an end behavior of a negative direction either because it can't go below the ground. We can't, I guess we could dig a hole and bury it, but that's not feasible when we're talking about it flying. So since the drone cannot travel for a negative amount of time, the function's not defined for values of x less than 0. And also there is no end behavior as x cannot approach the negative numbers. And as x approaches positive infinity, we can see that f of x is also approaching positive infinity because my drone is expected to continue flying higher. Little study tip. Assuming that the drone can continue to fly for an infinite amount of time and to an infinite altitude lets us analyze the end behavior. However, we realize that there are maximum legal altitudes that a drone can fly as well as limited battery life. You could be like my son. He was flying his drone the first week that we came back to school. We have a big 50-acre field full of soybeans. and he's flying it, having fun. I was in bed asleep. I'm a terrible parent. I had no idea he had went out at like 6 in the morning to fly his drone. He did not wake me up. I did not hear him. And he was out there flying it. I get up, my alarm clock goes off, go to get ready, and he's squalling. I'm like, what is wrong with you? His drone battery went dead and the drone crashed in the beans, and we still have never found his like $200 drone that my mom got him for Christmas one year. It's buried in the beans. It's hidden. Who knows? We tried to find it, but we couldn't. So important to remember, there is a limited battery life, but making these assumptions allows us to look at the end behaviors. All right, that sums up today's lesson, unless you would like to watch this beautiful little video of this flying drone. But that is all that I have for you for today. I hope this lesson didn't bore you to tears too much. If so, watch it when you go to bed tonight and it'll put you right to sleep. Have a great day, guys.